Okay, so welcome back. Today we have a couple of exercises on eigenvalues, eigenvectors, and eigenspaces. As usual, we'll first solve the exercises and take the chance to, while solving them, to review some bits of theory, and afterwards I'll give you the usual tutorial on how to write the clean, detailed solution for each one. So let's start. We have two matrices here, A and B, 3 times 3 matrices, and the first question asks, determine the eigenvalues of A and B. Well, eigenvalues, how do you get them? How do you define them? Well, let's say we give a practical definition here. So there are solutions of this polynomial equation. So determinant of A minus solutions, let's say solutions lambda. So you have this equation, and you just look at the solutions of this polynomial. So let's try, and in the first case, I mean A, let's put it, so this in our case is just 1 minus lambda 0 0 minus 2 minus lambda 1 minus 6 3 minus lambda. Very well. So you can compute. It's kind of easy. You can use the Laplace formula. Just have this times the determinant of this. So, well, it's kind of straightforward. So, yes, and I mean, after you compute, indeed. You compute indeed this, and this is like minus 6. So, well, what? Okay. Very good. So, I hope I'm correct. Yes, I think so. So this and this go away. So you have this. And so you can factor if you want. You can factor as follows. This is lambda 1 minus lambda and lambda minus 1 if you want. So the only solutions are like lambda equal to 0 and lambda equal to 1. Lambda equal to 0 has multiplicity 1, and lambda equal to 1 has multiplicity 2, actually. So, and I mean, but these are the only eigenvalues. And now, let's do the second. So, determinant let's compute it. Well, of course, I mean, this is a little bit sloppy, but I mean, I have to put this equal to this. Let's write like okay. So, well, so what is this now? Well, you have minus lambda. Okay, this is even easier because you have this minus lambda 1 minus lambda minus 1 0 0. Okay, me write determinant. Okay. Okay, very good. So it's just, I mean, it's an upper triangular matrix. So the determinant is just the product of the elements on the diagonal. So it's very easy now. It's this. Fine. Fine. Fine, fine, fine. Fine. Okay. So even in this case, you get from lambda equal to 0 or lambda equal to 1, but now 0 has multiplicity 2 and 1 has multiplicity 1. Okay, so far so good. Now the second point asks you determine a basis of each eigenspace of A and B. So first, what about eigenvector and eigenspaces? Let's just recall this. If you take an eigenvalue, first of all, don't forget, eigenvectors are always different from 0. In this case, let's say, in general, you'll have a square matrix, n times n square matrix, but in this case, n is going to be equal to 3. But no, I mean, just giving the general setup here, just to recall, such. Let me see an eigenvector. Let me see with corresponding. Okay. Let's just rewrite it. Sorry. So different from 0, this is important, don't forget it. Such that, with respect, I mean, if you take A as a matrix. So the interesting thing of eigenvectors is that if you apply your matrix to an eigenvector, then you get itself multiplied by the corresponding eigenvalue. So now you can define the eigenspace corresponding to and this is just this. So you take all the eigenvectors plus the 0 vector, which is not an eigenvector. And I mean, this is just a definition. And so actually to compute eigenspaces here, we just have to solve some linear systems. So it's nothing really new if you take just computations into account. So let's just do this. We have, for A, we have 2 eigenvalues, 0 and 1. So actually, well, it's worth observing that by definition, E0 is just So it's actually the kernel. So the eigenspaces, which are, by the way, subspaces of your Rn, are a way of generalizing the kernel if you want. In any case, let's try and let's find this eigenspace corresponding to this 0 eigenvalue. So you just have to solve the corresponding linear system. So it's just 1, 0, 0, 0, minus 2. I mean, it's not very difficult, but 0, minus 6, 3. Well, and from this you just get a linear system. You just get a linear system which is x equal to 0, and yes, minus 2y plus this is equal to 0. And I mean, if you look at this, I mean, this equation is not really necessary because it's just a multiple of the second one, so you can just find from here the conditions are just, let me see, just this. So the general element, the general solution has this form. So you have 0 for x, you have y, any y, and this one. So it's like yes, very good, very good, very good, very good, very good, very, very good. So you conclude from this, that E0 of A is just the span of 0, 1, 2, this vector. Very good. Let's go on and let's compute E1 of A. So you just have to solve this linear system. So, well, it's like just x equal to x minus 2y plus z equal to y, and minus 6y plus 3z equal to this. Fine. 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 So, yeah, you can rearrange things. So from this you get no condition. So you have this 3y, and the other, is it correct? Yes, the other gives the same condition actually. So if you go here, there is a minus somewhere. No, sorry. Yes, it gives the same condition. Gives precisely the same condition. Okay, so you just have this you have just this condition. So the general solution is going to be something like this: x can be anything, y can be anything, but the other is forced to be like. So you can decompose plus y 0, 1, 3. So you can conclude indeed that E1 of A is the span of these two vectors. Okay, very good. So we're there. Let's look at B. So E0 of B, you have to take your B matrix, which is like, well, can I copy it? I don't know, 0, 0, 0, 1, 0, 0, well, and 2 minus 1, 1. So I just have to solve I mean, it's nothing new here. This is, again, the kernel, so you have this. From this you get the linear system. Well, the first equation gives nothing. The second equation gives x equal to 0. And the third gives, taking into account, well, not taking into account this, but minus y plus this. So x is equal to 0 again. So you conclude just this is the condition, y is equal to, or if you want. So here the general solution is of this form. So 0, y, any y, and again, so this is 0, 1, 1. So you conclude that E0 of B is the span of 0, 1, 1. Good. The last one, so E1 of B. So E1 of B, how do you compute this? Well, same thing. Take the B matrix, 2 minus 1, 1, and just solve. I mean, they're just linear systems. Now we should all know how to solve this. So it's going to be, I mean, here you get 0 equal to x. Here you get x equal to y. And here you get 2x minus y plus z equal to this. Okay, but from this you get that it's also 0. So you find out x equal to 0, y equal to 0, and the z is equal to z, which gives no conditions. So again, the general solution is of this form. So it's 0, 0, any z. So it's going to be of this form, and you conclude that E1 of B is of the form, is the span of this vector. And we're done. So you have it. Okay, that was it. Just solving linear systems. Okay, now the third question is a little more theoretical, and it's about diagonalizability. So it asks, if possible, determine an invertible matrix S such that this composition, which is sometimes called conjugation, is diagonal. And also an invertible matrix T such that this is diagonal. So the same thing, the same question for A and for B. Okay, so let's address this. I have to add a page. Okay, so now we have to recall the theoretical results. So we know that a matrix, let me call it C, just not to use A and B again, is diagonalizable. And let me just n times n matrix C is diagonalizable. Is diagonalizable, okay, if there exists an invertible matrix S and a diagonal matrix. Diagonal matrix, you know what it means. It's just every element except the ones on the diagonal is 0. Such that, let me just, okay, if you want, S minus 1 CS is equal to D. Oh, well, just a caveat here. You can ask, well, if you take a 0 matrix like this, is this diagonal? Of course it's diagonal. Everything every element which is not on the diagonal is 0. I mean, the diagonal is also 0, but the thing is that, yeah, this is 0, this is 0. Well, just to say. And yes, this is the definition, but there is there are some nice criteria for diagonalizability, and one involves eigenvectors, eigenspaces, eigenvalues. So there is a test, well, condition, let's say that, condition C is diagonalizable if all eigenvalues are real numbers. Well, there is this thing that the equation which you use to find the eigenvalues is a polynomial. So, I mean, in general, not all polynomials have solutions in real numbers, but you have to require this. So, and also, how can I say this? Let's say this. There is a basis of eigenvectors, which means more practically, when you find the basis, plural, of all eigenspaces, you can combine to form a basis of Rn. There is something more here, namely since you should know from the theory that you can say that the eigenspaces are in direct sum, but I mean this means just that every vector you find as part of a basis of every. When you combine these bases of all eigenspaces, what you get is automatically a set of independent vectors. Since let's write that, since eigenvectors let's say since well, it's kind of not so easy to express this, but I hope the idea is here. So let me just try and express it a little nicer. So nicely. So how can I write this? When you find the basis of, okay. Yes. Okay, you can, well, since recall combining the basis of the eigenspaces gives a set, gives always gives, well, a set of independent linearly independent, of course, independent or linearly independent vectors. So it is enough to check that that the cardinality of this, well, let me say combined set of, oh, what did you do? Basis. Well, this is like, I hope you understand what I mean. This is just a set which comprises all these bases. So this set is precisely n. So you have precisely n like independent eigenvectors. This is perhaps better. Eigenvectors associated to different eigenvalues, of course. Yeah. So that was the theoretical recap, but actually now it's after you have it. Sorry, I'm not over, but there's something else to say. So when you have this and observation, if the above condition is satisfied, then you can take these kind of forced. So these are eigenvalues with multiplicity if necessary. And S, you can take it as, if you want, the columns of S. This is the basis of eigenvectors we discussed before. So if you want the n independent eigenvectors. So the important thing of eigenvectors and eigenvalues is that you can like put your matrix, if you like change the coordinates in some sense, you can put your matrix in diagonal form, which is very nice. And it's extremely useful. And in the future we'll see some applications too. But now it's kind of easy to see. Actually, this is a if and only if. Yes. Okay. I can say on the real numbers. We are always working on the real numbers. No frills here. Okay. So let's have a look at our setting. So we actually did everything already. So the first one, we found all the eigenspaces. So you get from the first eigenspace is this. So we had two vectors which are independent. It's a basis, and the other one, oh sorry, was that. So this. So you actually have, and this is independent from the other two because of the theoretical results. This is a different eigenvalues than one. So the corresponding eigenvectors have to be like independent to the other to the ones corresponding to the other eigenvalue. So if you take this plus this and this, you see that you have exactly three vectors. They are independent in R3, so it's a basis, and it's actually what we need. So to solve, actually the third for A, take S Well, I already forgot. So let me put the 0 first. It's not really important, but so 0, 1, 2. And then it's 1, 0, 0, 0, 1, 3. I hope it's correct. Let me just check this. So, okay. Okay, fine. So it should be okay. Zero, 1, 3. Was it good? Yeah, we hope so. We definitely hope so. Let me just check in my solution sheets. Let me see. Yeah, it looks good. Looks good. Looks definitely good. Yes, it works. So you can take this, and if then you take if then you take s minus 1, s inverse of s, I mean this composition, what you get is what? So this is the first the 0, and then there is the 1, but you have to count it twice. So this is the diagonal matrix which has the eigenvalues counted with multiplicity. Okay, and what about B? For B, well, let's have a look. But actually for B, what you have here is that you have one eigenspace corresponding to 0, which has just dimension 1, so one basis vector, and the other also has dimension 1. So you see, and these are the only ones, the only independent eigenvectors we can find. I mean, there are no more than 2 of them, let's say that, because these are all the eigenspaces. So the thing here is that we can't diagonalize B, and that's the reason. We can't find T. We don't have enough vectors. It happens, not all matrices are diagonalizable. There's something one has to remember. Okay, fine, and just the last one. So, tell if the following statement is true or false and why. There exists an invertible matrix U such that B is equal to this, like conjugation. So, let's see. I mean, how do you approach a point like this? Well, is it true or false? Well, let's see. What should our intuition be? Well, perhaps let's try and check what happens if we assume this is true. So, that B is equal to UAU minus 1. So, if B is equal to UAU minus 1. But A is diagonalizable. So call this D, and then A is actually this S, D, S minus 1. So you have U, S, D, S minus 1, U minus 1. And then from here you actually see that this is US, D, US minus 1. Recall S minus 1, U minus 1 is the inverse of US, not of SU. Okay, so what you see here is that if this holds, then then you could in principle define a matrix T like this and get that T minus 1 BT is diagonal. And this is a contradiction. Conclude such U can't exist. And yes, this was kind of a guess, but in general, you should think of this like conjugation operation here. It preserves quite a lot of properties. So if you start with a diagonalizable matrix and you do this operation, you still have a diagonalizable matrix. And actually also with the same eigenvalues, even more, actually with the same polynomial. I mean, this polynomial we started with, this polynomial is called the characteristic polynomial. And I can spoiler you that if a matrix is, if two matrices are in this relation, so if there is like, if you have one and you have this other one conjugated, then they have the same characteristic polynomial. So actually just the same eigenvalues. And okay. And that was the first exercise. As for the second one, let's see. So it's also about eigenvectors and eigenvalues. But here, as a general hint, which always holds, I'd say, well, never do useless computations. So let's have a look at this. First, for each I, say if AI is symmetric or not. Symmetric means that sorry, it's equal to X transpose. But I mean, here it's straightforward. You have to look at the diagonal, the elements which are not in the diagonal. If they are the same, it's symmetric. I mean, but it's just direct inspections. Yes, so all symmetric. So, and okay, the second, the eigenvalues of each AI, and if possible a matrix SI such that this is diagonal. Well, before starting doing computations like a monkey, let's have a look at this. Here you have three matrices, A1, A2, A3. They are already diagonal, because here you have zeros, here you have zeros, here you have zeros. And since they are already diagonal, of course they are diagonalizable. And which matrix can you use? Well, take S1 equal to S2 equal to S3 equal to the identity. Because, well, say identity minus 1, A1 identity, which is A1, is diagonal. And the same for A2, A3 here. I mean, it's kind of trivial, but still, it's important to not to start and do computations when you can avoid them. So actually the only, let's say, interesting one is the fourth. And for that we have to do some computations. And so let's do this. So let's take the fourth and let's compute this. So what is it? 2 minus 1 minus lambda 1, 1 minus lambda. Very good. So it's like what? Minus lambda 2 minus lambda minus 1 minus 2 lambda plus lambda squared minus 1. So from this you get lambda, the solutions are going to be 1 plus or minus its square root of 2. So yes, take the first, for example, 1 minus this, and the second is going to be this. So in order to find the matrix S, you just have to look at the eigenspaces here. So for the first one, so look at, let's say, a lambda 1 of A4, have to solve a linear system, which indeed is, well, you can also substitute. It's like true. You can also write this, of course. I mean, it's the same as writing. It's the same as writing true. Perhaps this is wrong, but no, it's okay. True 1, 1, 0 xy equal to lambda 1 xy. Just the same thing, okay? So here, just, I mean, it's just a few computations here, but nothing really bad. Okay, so here you should obtain something like this, 1, 1, and minus 1 plus this. So you can just compute. Fortunately, there is nothing tricky here. Fortunately, just some linear systems. We've been doing this for a long time now. Okay. Good. So this is just a linear system. So just like you can solve it any way you want. I mean, I'm lazy, so I'm just substituting stuff. So from here, you find out that y is equal to this. Okay. And if you substitute here, you actually find out that here it's going to be x plus let's just it has to be equal to 0, but if you look at this, it's just like it's just sorry, a minus b, a plus b, right? I think so. I think so, which is then a squared minus b squared. Oh, wait a sec. Something. Have something wrong here. I made something not really. Well, sorry, I copied. My bad. Yeah, that was it. Okay, so so it's like, yeah, but it's just computations here. Oh, come on. This is a -1. Wait. Okay. Sometimes it's boring, but one has to do this, unfortunately. Okay, and so if you want, it's this is not. I hope it's. Well, there's something very wrong here. Sorry. I mean, this is just, if you want, this is a way of showing you that computations can be kind of boring and lead you to stupid mistakes and make you lose time. So it's good that you avoid them as much as possible. So I hope this is now correct. Let me see it again. Yeah, definitely correct. But if you now substitute, okay, then you get what you should get is is -1 this, -1 minus, okay, fine. And so this is, which is, has to be equal to 0, but if you, this is an x here, so if you make this, if you do this, it's like just, so it's again 0 equal to 0. So as it has to be, the second one is just redundant. It's just the same as the first. So this is the only condition. We could have skipped this, but I mean, this is a check, another check that we are doing the right thing. So so the general solution is like this form. So you have x and -1 minus x, so it's like x1 minus 1. Okay, so E lambda 1 of A4 is the span of this vector. Okay, what about the other one? What about the other one is yes, so yes, E lambda 2 of A4. Okay, so again, you have just you can just substitute lambda inside of this. Instead, lambda 1 here, you put lambda 2, so you get 2 minus 1 minus square of 2, which leads you 1 minus, and then you put, yes, minus 1 minus. Okay, so this is the system we want to solve. Again, I mean, we could also conclude here by somehow like observing that the two lines are one of the can be obtained from each other by multiplying by some factor, which is probably some, I don't know, 1 plus square root of 2 or something like this. Not sure, but or with a minus somewhere. In any case, if you don't like to do this, you can just substitute. So this is going to be x minus, and again you can substitute here y is, and if you substitute, yeah, you again find x minus, and this is again 1. So this doesn't give any condition, this one, and so you conclude that the general solution is this. If you want to write like this, minus 1 plus. Okay. Well, x. Okay. So again, it's x times 1. Okay, so we conclude finally that the second eigenspace is actually the span of this vector, which is good. So indeed, we can find the S4. May put the eigenvalue, the lambda 1 first, the corresponding eigenvector first, and the other next. But it's then you can just put the two. So 1 minus 1 minus. Okay. And again 1 minus 1 plus. Fine. This is it. So the others were the identity, and this is the last one. So wait. Should be okay. I'm just checking. Yes. 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 Very good. It's okay. So, and the last point of the exercise is just more of a curiosity than a point. So, check if the columns of Si are orthogonal vectors. Just have to do the, like, and let's say S1, S2, S3, the identity. So you just have to make the scalar product between the columns of these SIs you found, and something nice happens. So the first for I equal to 1, 2, 3, then you get the identity. So it's like this, and indeed 1, 0, if you take the scalar product, is 0. As for this one, which is a little more complicated, 1 minus 1 minus lambda 2, 1 minus 1 plus lambda 2, and you do this, then what happens? You have 1 plus, actually if you want, minus, and you change the sign here and here. So it's actually 1 minus 1, which is again 0. And if you want a spoiler here, if you're interested, this is actually not it's not something which happened like without a reason. The point is actually when you have symmetric matrices and you try to diagonalize them, you can always find a basis of eigenvectors which are orthogonal. So even better than independent, they can be found to be orthogonal to each other. And this is nice, definitely. So yeah, that was it. I've actually done the fourth before doing the third. Well, as for the third, we have to compute AI to the 19th power. Well, sorry, I switched, but well, no big deal. It happens that sometimes you skip something and you do the other parts later. It's okay as long as you do everything, or you try to do everything. So, what about taking the power? I mean, the first ones are very easy because I mean A1 to the 19th power is just the identity to the 19th power. So it's 1 to the 19th, 1 to the 19th. It's just, you take the, and this again, this. So again, diagonal matrices, to compute the powers of diagonal matrices, you just have to compute, to look at what happens to the diagonal elements. So it's very easy. So it's just 3 to the 19th power, which is what it is. I don't know, but it doesn't really matter. And of course, the zero matrix remains 0 if you want. 0 to the 19th power is still 0. Okay, the only interesting one is this. So here, what you know is that what? So if you take, so if you take, S4 minus 1, A4, S4 is diagonal, but it's diagonal and it is what? It's actually the matrix which has on the diagonals the corresponding eigenvalues. So it has to have lambda 1 and lambda 2, which were actually 1 minus square and 1 plus square root of 2. I think so. I think it's okay. Should be okay. Should be okay. Should be okay. Yeah. Yeah. It should be okay. Should be okay. Yes, yes. So the thing is that now you can express this, or let's say you can express A4 as, by switching this like conjugation in this way, take S4, this diagonal thing, and S4 minus 1. And you should know that when you take this kind of strange conjugation operation and you take the power, then you can just take the power just inside. It's very easy because, I mean, if you want, just take the second, you see that these cancel out and you're left with just to see, and you can iterate. So it's like this: 19th power, this to the 19th power, and we have just to know what this S4 minus 1 is. I mean, since S4 is this, S4 minus 1, we have a formula, we can use it. It's perfectly allowed. It's a hint, so why not use the hint? Okay, so if S4 is this, let me just recopy it for my convenience, because I'm probably forgetting stuff, starting forgetting stuff now. So, okay, very good. And so to find the inverse, you can just compute the determinant here, which is, well, what is it? It's, let's first compute the determinant of S4, which is, yeah, minus 1 plus this, plus one plus, I think it's this, so it's 2, I think it's this. It should be okay, right? It should be okay. Should definitely be okay. I hope so. Oh, starts to be a little bit tired, but no worries, we'll make it. So, yes, multiply this minus 1 plus square root. True, you remove this, but you add. Yes, it should be correct. Okay, so the S4 minus 1 is this, and then you switch things a little bit. So you should put minus 1 plus this. On the diagonal you have switched things, and then you take the opposite. So it's minus 1 here and 1 plus. Okay, very good. So now if you want, you can really compute this thing. It's just a matrix multiplication now. And yeah, well, let's do this, but just for the sake of. So A4 is what? So have A4, which is, I hope I'm not messing up the one. I hope I'm not messing up the computations, which, by the way, are not that essential now. I mean, in principle, you could also leave it, and since the important steps are done, then you could say, well, this boring thing, let just a computer do it. Doesn't teach anything, indeed. So you have this, you can put this like here, and you have minus 1 plus square minus 1, 1, and here you have 1 plus. Yeah, okay. So, well, it's kind of boring, actually. Well, let me not do this. Let me not really do this. It's really kind of boring. I mean, you just have to compute everything. But, well, okay. Let me try, and I'll make mistakes, and just forgive me. I'm not assuring that this is going to be correct. Let the computer do this boring thing, but it's going to be better. So here. Fine. Huh. Well. And well, it's very ugly, but still. Well, I'm missing something also. No, it's not missing, but it's just here. Okay. Fine, and yes. So it's going to be minus this minus 1 plus. Well, this is nice probably, but plus. Yeah. Okay, and this is. And last one. No, the last two ones, sorry. So this minus plus, okay, and moreover, it's kind of, let's put plus here, plus, well, this is it if you really want it, and you can also simplify it a little bit, but yeah, it's not really essential. Just done this for the sake of completion if you want. Yeah, but it's not really important. You can, if you can make some symbolic calculator do this if you, I mean, yeah. It is what it is, but the point is that the important thing is that we managed to write this, and then actually doing this product is not really essential. So fine. So we've done everything, I hope. Yes, the fourth we've already done. So now time to finally write the solutions, and this time, fortunately, it's not going to take much time, because I'm choosing, given that most of the things we've done, many of the things we've done were just like solving boring linear systems. But it's not really essential if you have them in some draft. So here, which is not that bad, you can just attach it and refer to it. Perhaps it's not like probably the best. You're not really like, it's not really very clean, but still, they're not essential computations. And the important thing is that we are going to concentrate on the essential things while writing the solutions. At the same time, referring back to the drafts whenever it's just some direct computation, or like solving some linear system, which is like, here you can, if one looks at it, it's not really interesting, but if they really want to look at what you've done, they can, even if it's not actually interesting. So let's write a concise solution today, given that most of the things, as I said, were just like computations. I mean, just to be clear, I'm not advising you to not to detail things. But I mean, here, if you really want to rewrite everything, it's going to take a lot of time. And so when you're doing an exam or something like this, time management is also important. So at some point, like here, it's okay and also kind of useful to choose what to write down in a solution. And if you want to refer back to the draft, to computations you've done, you're pretty confident they're correct, so you don't want to recheck them, you're pretty confident they're correct, and you think, which now is the case, and you think that conceptually they're not really interesting, then it's okay to refer to the drafts and not to include them in the detailed solution. So let's take this philosophy and let's write the solutions. So nicely. So first exercise, what was that? Determines the eigenvalues of A and B. We'll just give the reader the concepts, avoiding to rewrite all computations and referring them and refer back to the drafts. Okay. The obtained. So which yield well, 0, 1. Well, let's say that we get, let's say that at least we write down the polynomials. We have just the final. See, I mean, writing solutions is not really hard science. It's making choices, but choices can be discussed. And the thing is, what makes a solution a good solution to something which is nice to read is actually is actually your willingness to make the reader comfortable and get him to understand what you're doing. So here I'm choosing that it's kind of nice to write down the polynomials for the reader. So let me copy. No, that's not a copy. Huh. Well, let me check if it's correct. Uh-huh. Okay. Okay. Well, you can also write minus lambda minus 1 squared. Sorry. Which yields and here it's kind of different. So it was, sorry for this backtracking, but well, there's an error here. It's like this, which is actually lambda squared. Okay, lambda squared 1 minus lambda. Fine. I mean, it's nice to write the polynomial because you can see that, I mean, you see the multiplicities, which are kind of an interesting information. So it's a good thing. Let's say it's a good thing to write down the polynomial and not just the solution. We can make, and we can put a reference, see the drafts for the computations. Okay, so this is it. That's for the first, okay. And as for the second, I mean, here, there's actually nothing to say more than like stating the results. So the fact that the eigenspaces are these ones, and we can just refer back to the draft because it's not really interesting. So we can write we can write after computations, see we get, and you can just E0 lambda is equal to span E1 am I writing it? Yes, 0, 1, 2, 1, 0, 0, 0, 1, 3. Okay, and here you can is it correct? Wait, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1. Okay. Zero, zero, one. Very good. Fine. Okay, this is it. And for 3, so we can write this diagonalizing matrix S for A is given by zero, 1, 2, 1, 0, 0, 0, 1, 3. Since we have three independent eigenvectors. Okay. Okay, and we have to explain that we have no diagonalizing matrix T. On the other hand, for B, we found just true let's say we couldn't find three independent eigenvectors. And I'm being a little bit redundant here, so if you take the no, it's okay like this. Okay, so B is not diagonalizable. And there is no matrix T such that T minus 1 BT is diagonal. Okay, let's go on for the fourth point. Okay, and we just say this statement is false. Is false, and then you explain. Indeed, assume that B U A U minus 1 for some invertible U. Then you, from the fact that S minus 1 AS equal to D is diagonal, we get A equal to S ds minus 1 and B equal to yes, US D U minus 1 no, sorry, S minus 1 U minus 1, which is US D US minus 1, which contradicts the fact that B is not diagonalizable. Okay, this is it for the first exercise. And this is a neat solution, but we avoided rewriting all the straightforward computations. I mean, this is just computing determinants. It's nice to have them written down as polynomials because you get the multiplicities of this lambda and these eigenvalues. But yeah, it's not really interesting unless you really want to show that you know how to compute determinants. But yeah, if you do it wrong, then you get wrong results. So and here you recall that it's just linear systems, and in any case we are not really avoiding writing the computations. We're just avoiding copying them, and we're just referring them as the drafts. We attach them so the reader, if they want, they can go back and go through all these computations, but I mean, while accepting that they're not really interesting. So it's probably okay to, I mean, it's definitely okay to not to include them in the final solution, and instead referring to them in the draft. So it's a nice thing you can do, and it's safe. It's definitely safe. When you do boring computations, and you don't want to and you don't want to recopy them, you can refer to them in the final solution, and it's okay, as long as you're not avoiding conceptual and interesting points the reader should want to know in the final solution. Okay, so that's for the first one. So let's go to the second one then, which is going to be like hopefully as quick as the first one. We're going also to avoid some computations. Exercise 2. So. Okay, say if AI is symmetric or not. Fine. By direct inspection, this is really straightforward. By direct inspection, we see AI let's say that AI is symmetric for all I from 1. Okay, this is it. So the second point, find the eigenvalues of each AI, and if possible, a matrix Si such that, yes, this is for this here it's interesting for A1, A2. Oh, let's say that. Let's give this information. A1, A2, A3 are diagonal matrices. So the eigenvalues are given by with their multiplicity by the terms on the diagonal. We don't really have to say that then it's 3, it's 1, it's 0. I mean, the reader is not so dumb. They can go there and they know what diagonal means. They can go there and look for themselves that it's like 1, 0, or 3 or whatever for each of these, like A1, A2, A3. For A4, we have here, we just detail a little bit. So very good. So wait a sec. Okay, you get this. From which we get the eigenvalues number 1. Okay, 1 minus 1 plus. Okay, I think it's okay. Let's see. Is it, yeah, 1 minus 1 plus? Fine, much fine. Okay. Okay, so is this everything for the second point, or do we need something else? No, eigenvalue, and if possible, a matrix Si such that Si AI, okay, is diagonal. Okay, so okay, let's go on for A1, A3. we can set S1 equal to S2 equal to S3 to the identity matrix, since they are diagonal already if you want. For let me just be a little more detailed here. Wait. So, okay. As diagonalizing my matrix, okay, let's write this. For A4, we find out, see the drafts, that S4, which is the what? This okay. Nicer is a diagonalizing matrix. Okay, and okay, this is it. The third, which is like, yes. Okay. So, using the hint, we get, I mean, hopefully it's correct. Well. Okay. Hence, okay, now since S4 minus 1 is equal to lambda 1, lambda 2, so this we conclude that A4 to the is equal to the, okay, is it correct? Yes, it is. I mean, it's not really interesting to oh, there's no room here, but I don't want to open a new page. Okay, see the but I need a new page in any case. See the draft for further details. This is something you can say. Well, but 19th power you need here, which then, well, that I forgot. Okay. Nineteen. Okay. Fine. Okay, this is it. And I think it's okay. Check if the columns of Si are orthogonal like this are true. Okay. So here we can compute for S1 we have, I mean, this is a cheap computation. You can also write it for S4. Well, what is S4? Okay, is this thing. Yeah. Sure. Is equal to 1 minus indeed okay, and this is it. So yeah, this is a nice solution. We avoided the boring computations we had to do, but we still referred back to them as part of some drafts you would still hand in a hypothetical exam. And it's okay. It's perfectly fine to do this. So yeah, I hope it's clear. The way we've written down the solution today was like a choice of avoiding some boring computations, but still having them in the draft, so being able to refer to them, which is a safe move, and also choosing to write down what we decided to be the most interesting aspects and steps of each solution. So yeah, as always, as I said, writing a solution is like there's not a specific rule. You just have to think what is the best for the reader. You can try some empathy if you want. What I would like to read. What solution would I like to read if I were myself the reader? And constantly asking this then leads you to write down something which is nice and clean, and also like perhaps not full of, like in this case, not full of computations which are not really interesting, but still we can attach and refer to them. So there is completeness we always have, which is a good thing. Okay. So that's all for today, and okay, so well, we see you again next week.